Hi, this is S. Lakshmanachari, working as Assistant Professor in Department of Cybersecurity, Institute of Aeronautical Engineering, Hyderabad. In this lecture, we are going to discuss the problems on bus and address lines. So, before going to the problems on bus and address lines, we will we will go through the details of the basics of the bus and address lines. So, basically, the computer it can be used to perform various operations. So, the computer is an electronic device that can be programmed to accept the data, process it, and generate the results. So the computer is made up of some electronic components, and it is programmed to accept some input data from the various input devices. After accepting the input data, then it will be the accepted input will be processed by the CPU, and then it will generate a results. And the most computer systems, from the embedded controllers found in automobiles and consumer appliances to the personal computers and mainframes, have the same basic organization. So even if you consider any small appliances that include the embedded controllers and automobiles and consumer appliances to the personal computers and the mainframes, they are having the same basic organization. So mainly, if you dig into the internal structure of the internal organization of the computer, mainly it has three primary subsystems or components. So that are CPU, central processing unit, memory subsystem, IO subsystem. So these are the three main primary subsystems or component. So first one is CPU. So the CPU it performs various operations. So the CPU it consists of three parts. The first one is the ALU, arithmetic and logic unit. So this ALU it is responsible for performing various arithmetic and logical operations. And coming to the control unit, so control unit it is used to generate some timing and control signals, because the computer it consists of various modules. So in order to function all those modules properly, it requires some synchronization and timing signals. So the synchronization and timing signals are generated by the control unit. And the next one is the registers. So in order to perform various operations, then we require some registers. So register is nothing but a group of flip-flops. So in that registers we are storing some information. So on that information or on the data, we are performing this arithmetic and logic operations. So arithmetic operations are addition, subtraction, multiplication, and division. Similarly, the logical operations include and, or, XOR, not, complement. So these are all the various arithmetic and logic operations. So the next subsystem is a memory subsystem. So memory is one of the important resource in the computer, because we are storing so many programs and the data inside the memory, because the CPU it cannot store the large amount of binary data inside the computer, inside the CPU registers, because we have a limited number of registers. So that's why we could not store large amount of binary information. So that's why we can store the large amount of data in the memory subsystem. And third one is the IO subsystem. So this IO subsystem it provides a facility to interact with the outside world. So that means we are connecting several input or output devices with the computer. So in order to for the especially this IO subsystem, it is used for communication purpose with the external world. That means the computer can accept the input data from the input devices. Then the CPU will be process that accepted input data. Then it will produce a results. So the generated results will be given to the output device for the sake of the user. Okay. For the benefit of the user. So all this. So just before we have seen various modules. So all these subsystems function together as a single unit to deliver the desired output. So these are the three main subsystems. So these three subsystems they will form as a single unit that is called computer that can be used to perform a specific function or in order to deliver the desired output. So this is a basic computer organization. So here you can see, so already we have seen three important subsections. The first one is a CPU, memory unit, and input-output subsystem. So CPU again it consists of three parts: control unit, arithmetic unit, and we have some registers. So registers are internal to the processor. And coming to the each of these components connected through the buses. So all these modules they are connected through using a buses, using the bus. So what is bus? So bus means physically a set of wires. So the components of computer are connected to these buses. So just before we have seen, so CPU, memory subsystem, IO subsystem. So all these various subsystems are interconnected by using these buses. So bus means a group of or set of wires. Okay. So these buses are mainly classified into three types. First one is a address bus, data bus, control bus. These are the three main types. So what is address bus? So the address bus, a set of wires that can be used to carry the address information. So that is called address bus. Data bus. So a set of wires that can be used to carry data. That is called the data bus. And control bus. So a set of wires that can be used to carry control signals. So we have different control signals like read, write, reset. Like that, some control signals are there. So all that control information will be carried by a set of wires. That is called control bus. So as the complexity of the computer system increases, so as the complexity of the computer system increases, it becomes more efficient at using the buses rather than direct connections between every pair of devices. So if we could make direct connections between these devices, we require more number of wires. So that means if the more number of wires are there, then the complexity of the system will be increases, and also power consumption increases, cost also increases. So these are the various drawbacks by using direct connections between the various devices. So to overcome the drawbacks, we are using a method called bus. So by using this bus, we can reduce the complexity of the system, and also we can reduce the power consumption. We can also reduce the cost of the system. And these are the generic organization of these component as shown in the figure. So these are how various modules are connected using the bus. So just before we have seen, we have three types of buses: address bus, data bus, control bus. So the address bus is connected from the CPU to the memory subsystem as well as the IO devices. So IO devices and memory subsystem CPU, every device it is having some address bus. So all that address buses will be connected. So this is a main address bus. So it is a unidirectional. It is a unidirectional from the CPU to the memory subsystem, because the memory. So memory it consists of various memory locations. So like this. So the memory is divided into various memory locations, and each memory location it is identified with a unique address, some address. Okay, so like this, every memory location it is identified using a address. So for that purpose, we have a address bus. So this address bus which carries the address. So that means from which location we are reading the data or writing the data into the memory location. So this is a unidirectional from the CPU to the memory. And second one is a data bus. So data bus is which carries the data, Whatever the data the CPU wants to process, that data will be carried by the data bus. And the data bus is a bidirectional. So it is a unidirectional. That means it is a bidirectional. That means from the CPU to the memory as well as memory to the CPU. Third one is a control bus. So control bus also it is a bidirectional. So from the CPU to the memory subsystem. Similarly, from memory subsystem to the control bus. So coming to the I/O subsystem. So the I/O subsystem it consists of various input devices as well as output devices. So every I/O devices it is having three types of buses. One is the address bus. Second one is a data bus. Third one is a control bus. So all these buses are connected to the respective buses. So the address bus of the I/O device will be connected to the address bus of the CPU. Similarly, the data bus of the I/O device will be connected to the data bus of the CPU. And similarly, the control bus of the I/O device will be connected to the control bus of the CPU. So like that, we are making all the connections. So coming to the problems, so the first question is a word addressable computer has 1 GB of memory and the word size is 64 bits. Assuming there are 80 control lines and 40 interrupt lines, how large is the system bus? So in the problem they are given the word addressable computer has 1 GB of memory. So that means it can address maximum of 1 GB and the word size is 64 bits. Okay. So the maximum memory capacity is 1 GB. So if you convert into the bytes, 1 GB divided by 8 bits. 8 bits means 1 byte. So if you convert into bytes, then it will give 128 megavolts. 128 megavolts. That means 128 mega memory locations are there. Okay. So if 128 megavolts are there, then in order to represent that 128 megavolts, we require 27 bits because this is a memory capacity. This is a number of memory locations. So the number of required bits to access that memory is log 2 of 128 mega. So it gives around some 26.93. So the nearest integer value will be always we are taking a rounded value. So that's why the 27 is the 27 bits. So that means by using 27 bits address lines, then we can address 128 megavolts. So the address bus size is 27 bits. Okay, and coming to the word size is 64. That means the number of data lines are equal to 64 bits. 64 bits. And coming to the control bus. So we have three types of buses. One is address bus, data bus, and control bus. So already we know address bus is 27 bits, data bus is 64 bits, and coming to the control bus. So the control bus, we have 80 control lines and 40 interrupt lines. So these are all carried by the control bus. So that means the control bus it consists of 128 lines because 80 plus 40. So that means 128. So 128 lines are there in the control bus. So what is the total system bus size? So total system bus size is equal to address bus size, data bus size, and control bus size. So by adding all those lines, it gives the system bus size. So 27 plus 64 plus 120. Okay, 211. 211 lines. So total we require 211 lines for this particular system. So this particular system bus, it should have 211 lines. Okay. Next one. A microprocessor has a data bus with 64 lines. So the data bus with the 64 lines. That means the data bus lines, the data bits are 64 lines, and an address bus is 32 lines. So address lines are 32 and data lines are 64. So calculate the maximum number of bits that can be stored in memory. So we need to find out the maximum number of bits that can be stored in the memory with the data lines are 64 bits and address lines are 32. So the amount of blocks that could be located is, so we have the address bus size is 32 bits. So with 32 bits, using this 32 bits, we can access up to 2 power 32 memory locations. So that means 2 power 32. So 2 power 32 locations we can access. And now since the data bus has 64 lines, so each block size is 64 bits. Each block size is 64 bits. So that means in each memory location we can store 64 bits, each memory location. So that means, see here, so the memory will be like this. It is divided into several memory locations. Okay, so total these memory locations are 2 power 32. 2 power 32. And this is a one memory location. So in every memory location we can store 64 bits like this. 64 bits we can store. So then calculate the maximum number of bits that can be stored in the memory. So this is the maximum bits, 2 power 32 into 64 bits we can store. Okay, so 2 power 32. So 2 power 32 means 2 power 30, that is equal to 1 GB. 2 power 30 is 1 GB. 2 power 31 is equal to 2 GB. 2 power 32 is equal to 4 GB. So that means 4 GB of memory we can access using 32 address lines. With and the size of the database is 64 bits. Okay. So these many bits we can store in that particular memory. And the following memory units are specified by the number of words times the number of bits per word. How many address lines and input-output data lines are needed in each case? So we need to calculate the number of address lines and the data lines for that particular memory. So first one is the 1K by 16. 1K, 1 kilobyte into 16. So the first it represents the first number, it represents the number of memory locations, and the second one it represents the word size. That means how many number of bits that we are storing in the every memory location. Okay, so 1 kilobyte means for 1 kilobyte we require 10 address lines. So 1 kilobyte means 1024 bytes. And 1 megabyte means 2 power 20. So that means with 20 address lines, we can access up to 1 megabyte of memory. So 1 megabyte is equal to 1024 kilobytes. And 1 gigabyte. So 1 gigabyte we can access by using 30 address lines. So 2 power 30. So that means we can access up to 1 gigabyte. On 1 GB, we can write in terms of megabytes, 1024 megabytes. So these are the information in order to solve the above problem. Okay. So first one is 1K by 16. 1K by 16. So we are going to find how many address lines and data lines are required to access this 1 kilobyte by 60 bits. So the number of words in memory unit is 1k. So number of words are 1 kilo. That means 1024 words. 1024 words. Okay. So that means for accessing 1 kilobyte, how many number of address lines we are required? So just before we have seen. So for 1024 bytes or 1024 words, we require 10 address lines. 10 address lines. Okay. So 10 address lines are required. And the number of input or data lines that are needed are 16, because this is a number of data lines, 16. Okay. So here you can see how with the address lines, 10 address lines and 16 data lines, how the memory looks like. So this is a memory. Here you can see these are the memory contents. So how many memory locations are there? So 1024. 1024 means the memory locations always starts with the 0. So this is a decimal notation. So 0 to 1024, because the last memory location is n minus 1. So where n is 1024. So 1024 minus 1, 1023. So this is 1023. So this is a decimal notation. So if you represent the same in the binary, so 0. So 0 means it represents all zeros. So 10 zeros. 1 represents 9 zeros, and LSB is 1. It represents 1 decimal. So like that, all the values can be represented in both binary as well as decimal. So you can see this. So this is the data. So how many number of data is there? 16 bits are there. 16 bits. That means in every memory location, we can store 16 bits of information. Okay. So for this particular memory, it requires 10 address lines and 16 data lines. Next one, 64K by 8. 64K by 8. So 64K means 65,536 words. So that means 2 power 16 words. So in order to access this 64K, we require 16 address, because 2 power 10, that is equal to 1 kilobyte. 2 power 11, 2K. 2 power 12, 4K. 2 power 13, 8K. 2 power 14, 16K. 2 power 15, 32 kilobytes. 2 power 16, 64 kilobytes. So how many number of address lines we require in order to access 64K? 16 address lines. Okay. So 16 address lines are required to access the 64. And how many data lines are required? So data lines are 8. So data lines are 8. Okay. So if you look into the memory, okay. So see here. So the starting address, so decimal notation. Decimal notation. So starting address is 0. What is the maximum address? So maximum address is n minus 1. So that means 65,535. So these many memory locations are there. So in every memory location, how many number of bits we can store? We can store 8 bits. We can store 8 bits. So like that 0, 0. So this is 8 bits. 8 bits. So like this we can store. Okay. So next one is 16 megabytes into 32. Okay. So 16 mega means 6 crores 7 lakhs 8,864 words. Okay. So that means we require 26. We require 26 address lines in order to access 16 mega. So that means 2 power 20. So that is equal to 1 megabyte. 1 megabyte. So 2 power 21, 2 mega. 2 power 22, 4 mega. 2 power 23, 8 mega. 2 power 24, 16 mega. Okay. So here 16 mega. So 2 power 24. That means how many address lines are required? 24 address lines. So 24 address lines are required. Okay, so 16 mega here. Okay, sorry, here 16 mega is there. 16 mega means 24 address lines are there. 24 address lines. Okay. So for 16 mega, so we require 24 address lines. Okay. And the number of data lines are 32. 32. Okay. And coming to the 4 GB into 64. So for 4 GB, it requires 32 address lines because 2 power 30, that is equal to 1 gigabyte. 2 power 31, 2 gigabyte. 2 power 32, 4 gigabyte. So we require 32 address lines for accessing 4 gigabyte memory. And the data lines are 64. Okay, so in this way, we can find out the number of address lines and data lines required for that particular memory. And draw a memory map of system with 12-bit address bus, dividing the memory space into 2K blocks, indicate the hexadecimal address of the first and the last address in each block. So, draw a memory map. So, we are going to draw the memory map of a system with 12-bit address bus. And okay, so how many number of address lines are there? 12 address lines are there. 12 address lines. Dividing the memory space into 2K blocks. 2K blocks. That means the size of each block is 2 kilobytes. Okay. So that means if the number of address lines are 12, then we can access up to 2 power 12 memory locations. So 2 power 12. So 2 power 12 means 4096 different addresses. So 40. So this is a memory. Okay. So that means total we have a 4096 different memory locations. So starting from 0 in a decimal representation, 0 to 4095. So these many memory locations are there. So these entire memory locations, we are dividing the memory space into 2K blocks. So that means we are dividing 2K blocks. Okay, so 2K. That means this is total 4K. So we are dividing entire this memory space into 2K. That means we are dividing this entire memory space into two parts. So we are dividing into two parts. So 2K. So we are going to draw the memory mapping for this 2K and this 2K. Okay. So each block is 2K in size, which means there are total of 4096. So total 4096 memory locations are there. So that we are dividing each block with 2048. So if you divide that with 2048, then it gives two blocks. So we have two blocks. This is first block and this is a second block. So for every block, we need to find the starting address and ending address. Okay. So total we have two blocks, block 0, block 1. Block 0, block 1. So what is a block 0? So block 0. So block 0 starting address and ending address. So here total we have 12 address lines. 12 address lines. So in order to find see. So this is block 0. This is block 1. Block 0, block 1. So for the block 0, what is the starting address and what is the ending address? So total we have 12 address lines. So in order to find the starting address, so 12 address lines will be equal to 0. So that means 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So these are the 11 address lines. So 4, 4, 8, 3, 11. So total 11 address are. So for the starting address, all address lines will be 0. For ending address, all address lines will be 1. So 1 means Okay, so if you represent in hexadecimal notation, so this is equal to 0, 0, 0. If you represent this in hexadecimal, 7FF. So this one. Starting address is 000 and ending address is 7F. So 7FF in hexadecimal. Similarly, for block 2. So what is the ending address of the block 0? 7FF. 7FF. So what is the next address? So the next block, it starts with the next memory address. So what is the next memory address? So the next memory address is a 8800. 800. So 800 means 1 triple 0 0 0. So this is a starting address for the block 1. What's the ending address? Ending address will be all ones. This is the ending address. So this is equal to F, F, F. So this is the ending address. Ending address. Okay, so this is block 0, this is block 1. So in this way, we can derive the memory map for the particular memory. So in this memory, block 0, it spans from address 000 to, so 0x000, it represents that the address notation is in the hexadecimal. So x represents the hexadecimal representation. And the block 1, it spans from address 800 to FFF4. Okay. So each block, it contains 2048 addresses, and the entire memory space is divided into these two blocks. And a microprocessor has the data bus with 64 lines and the address bus with 32 lines. So the data bus is 64 and the address bus is 32. The maximum number of bits that can be stored in memory. So the maximum memory is address lines are 32. So that means the maximum number of memory locations would be 2 power 32 into the data lines are 64. So these many bits we can store in the memory. And the last question. A microprocessor can support maximum question 6. A microprocessor can support maximum memory of 4 GB where the memory is word accessible. A word is equal to 2 byte. The size of the address bus of the processor is at least dash the bits. So the maximum memory is 4 GB. Maximum memory is 4 GB. So see here. So this 4 GB we can write 4 into GB. So in this lecture we have discussed about the basics to the bus, and also we have discussed various problems on the bus and the address lines. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.